Hello? Hello?
My name is Carlos Beltran. I'm from the Aerospace Corporation, and my presentation will be on single-bit upset simulation. So here's a brief overview of the presentation. First, I'll go into the background behind SEU simulation and why we're doing it. Then I'll go into the implementation of the SEU program, which I call Memogressor, which is still up for debate. I'm not sure if I like that name. Then I'll move on to some standalone testing, which I did before moving on to some Hill simulations. And then I follow that with integration to Hill simulations. It's worth mentioning that this presentation is a little shorter than I previously imagined because in order to have this presentation approved, I need to remove some of the Hill simulation testing that I did. And then I'll move into any of the future applications for Memogressor. So Aerospace developed a new capability to inject single-bit upsets into targeted memory locations. So currently, Memogressor can target virtual memory addresses, but in the future, I am working on also targeting physical memory addresses. So it provides a more test-like-you-fly hardware-in-the-loop flight software testing capability. So up until this point, we haven't had a good option when injecting single-bit upsets into an end-to-end mission. We have ways to fail sensor feedback from the dynamics into the flight software, but nothing like a single-bit upset. So SEUs, what are SEUs? So SEUs are a result of radiation hits flipping the bits and corrupting the memory of the flight software. So there's been research done by other departments that show that most radiation hits occur in the Van Allen belts, and most of the radiation hits affect single bits, and it's quite rare for radiation hits to affect multiple bits within a memory address, so it's really precise. Aerospace has developed, again, this tool called Memogressor, which is still up for debate. It provides the capabilities to inject temporary or permanent SEUs. So a temporary SEU is more of a non-persistent radiation hit. So what this means is that on the first access to either a load or a store from the flight software for flight software variables will actually read or write corrupted data, but every subsequent read or write after that will be nominal. And a permanent SEU is more of a latching scenario where a radiation hit affects the code on the hardware level, so every load or store word at that flight software memory access will result in corrupted data being read in or written. So it enables analysts to verify the flight software response in their various failure conditions. So it allows developers to test, to inject random errors into their flight software and see how their flight software reacts. It allows them to test their the fault-tolerant systems. So for all our testing, I use the ARM-based processor. Here's the general CPU architecture of the system. So you have your DRAM, which all your flight software variables will live in. They'll eventually get loaded into your memory management unit and eventually into the L2 cache and then eventually to a register file, which eventually you'll have an ALU operation or some type of multiplication. And eventually they'll get propagated into your GNC processing or whatever process you have running. So the point of the Memogressor is performing a fault injection by flipping a single bit in regions of memory that will simulate the scenario where an uncorrectable ECC memory page is ultimately loaded into the CPU register file, which could potentially propagate into GNC processing and then cause the flight computers to become unresponsive. So here's an overview of how it'll work in a Hill simulation. So you have the client application, which most likely would live on the Dynamics workstation. So the client application is in charge of initiating all the messages that is received by Memogressor, which Memogressor is a daemon process which runs on the flight software. So the client application uses protobuf and UDP because they're fairly ubiquitous. A lot of people have been mentioning protobuf is very it's useful in serializing and deserializing data, and UDP is fairly easy to do for socket programming in any language. So the Memogressor is running a blocking statement on the flight computers. So this allows you to sleep until it receives a message from the client. And once it receives a message from the client, it'll attempt to inject the error using a series of system calls, including ptrace. So here's a general overview of the implementation of how Memogressor works on a Hill. So you have the client, which is encapsulated in your Dynamics model, and then that sends a message over UDP through protobuf that includes arguments such as the PID, the address, and the SEU type. The SEU type is either a soft or hard watch point, which is a temporary or permanent SEU. So the Memogressor is running on the flight computers. It's also worth mentioning that Memogressor can also run on localhost, but for ease of use, it's easier for us to run it on the dynamic side of the client. So the Memogressor receives the message from the client, and once it receives the message, it goes to inject the error. So the first step in injecting the error is the Memogressor attaches to the PID. This is done through use of ptrace calls. And once the flight software process you are targeting is halted, the Memogressor sets a watch point using the ARM debug registers. So you're limited to 4 watch points at a time. This is a ARM debug register limitation. Once the watch point is sent, the Memogressor continues the flight software process, so it continues as normal. And Memogressor will wait for that PID, so eventually the flight software will access that variable you set a watch point on. And when that variable is accessed, the flight software will actually be halted by that watch point, and a SIG trap will be sent to the to Memogressor. And then Memogressor, once it receives that SIG trap, you're allowed to corrupt the data. As I mentioned previously, most of the radiation hits affect single bits, but we also added the capability to corrupt the whole memory address just for testing purposes. So once that memory is corrupted, the Memogressor detaches from the process that you've set the watch point on, and the flight software executes normally, and so it'll actually propagate that error corrupted data that you injected. So the flight software doesn't know that anything actually happened. So it's as if the flight software read or write corrupted data, simulating a single event upset. So based on whether you're using a soft or hard watch point, if you're set a soft watch point, you'll go back to the Memogressor in the sleep state where it's waiting for a message from the client. If you're setting a hard watch point, it'll go back to setting the debug registers to set a watch point, and this will continue for the duration specified by the client. So for standalone testing, before I went into Hill simulations, I used a standalone attitude estimation program from a different department. I focused on the struct right here, which contains quaternion estimates. So the struct here encapsulates both read-write memory and constant read-only memory. The state memory can be read in and written to at any time. In this example, the fields Q0 through Q3 are the current estimated quaternion of the fake system. On the other hand, constant memory is used to hold immutable data, things like one-time tuning configs, mathematical constants, and other things like that. Sample frequency is an example of this. So the fake attitude estimation program has several fault sensitivities. Here are a few. The first is the quaternion must be normalized, should never be all zeros. Denormalized quaternions will propagate and persist, causing bad estimates. The sample frequency is marked const, and there's no sane C compiler that would allow the program to manipulate it. The developer is relying on the hardware system software to ensure that this value is correct and unmodified. And the third of the last is the bit flip in the programs.txt symbol table section could lead to undefined instruction, prefetch abort exceptions, either by direct instruction execution or indirect branching into the weeds. So for my standalone testing, I worked on targeting the first sensitivity. So I added a variable to the quaternions, so the quaternions will divide by this new variable, which I call this should always be 1. So as long as it's 1, the quaternion estimates would be calculated as nominal, but if it's ever set to 0, then you'll have a divide by 0 scenario. So this is the log of the test I did. So at the top right, you can see that that's the log of the fake attitude estimation program, and the log below that is the log of the Memogressor. So right here, you can see that the client actually sent a message to the Memogressor, and it's actually received the message. You can see some variables here, the arguments, the address you're trying to access, which is the address of this should always be 1. The access length, that's the memory size of the variable, the bit position. So you can target any bit position in that memory variable you want to target. So once it receives the message, it actually tries to insert the watch point. So you can see it's attaching to the process. It tells you how many watch points you have remaining of the 4. And once the watch point's set, it remains in this wait PID. And once the flight software tries to access this variable, the Memogressor attempts to corrupt the data. So you read in the 1, which is correct, because that's what this should be 1 was initialized to. And I actually try to override 0, so this is what's happening here. So you can see before the single event, the injection occurred, the quaternion estimates were calculated correctly because this should be 1 is 1. And once the corruption happened, you could see the quaternion estimate estimates were calculated incorrectly because there was a divide by zero scenario. So once I finished with the standalone testing, I moved on to hill simulations. So this is where I had to remove a good amount of my testing for hill simulations for security reasons, so I'll briefly go over a little bit of what I did. So MemRegressor will run along the flight software during an end-to-end mission run. The flight software I modified to create a log of the variable addresses. So theoretically, you can just target any addresses you want in the flight software, but for my own testing sake, I create an output log of all the variables that are accessed by the flight software. So this allows me to target specific variables in the flight software. And I was to verify that the single event upset program was working because I was able to check telemetry after the mission and verify that whenever I ejected the error, whether it's hard or soft, that it was actually doing what it was supposed to be doing. And also the dynamics is modified to use a client SCU injection capability, so developers can just call an injection function call that can inject errors whenever they want into the mission, into any flight software process that they want. So for future Hill integration, I want to add provide options for a user that can send a config file for end-to-end mission runner, whether that be JSON or any other type of file. So they can specify at T2000 into the mission that they want to inject 4 watch points at these addresses, and then whether they're soft or hard, they will exit on their own, and then the flight software will return to nominal. So one of the main concerns I had when initially running the MemRegressor alongside a real flight software is the time it takes to insert the watch point, and corrupting the data may be too long to stop the flight software and may cause flight software to fail or become unstable. So this past week, I've been able to run multiple Hill runs, and I've seen no issues in terms of timing. So the MemRegressor does not affect the timing at all of the flight software. I think when MemRegressor is actually running, it uses less than 0.1% of the flight CPU utilization. So there's been no concerns in terms of that, I've realized, in the past week. So in conclusion, this tool can be done by leveraging low-level debugging capabilities. This is a relatively light program because it's mostly just using various system calls to operate. There's no heavy processing that's being done. The Aerospace Corporation develops SCU simulation capabilities currently being used in Hill testing. So like I said, over this past week, I've been doing multiple Hill runs, and it's been working really good. So this capability can be adapted to other architectures besides ARM. So initially, I started on x86, but then I eventually moved over to ARM, and then this can be propagated to other architectures as long as you're able to set watch points using the debug registers. So in addition to SCU, this capability can be used to corrupt system feedbacks to simulate various sensor and communication failures. So instead of injecting single event upsets into random places into the memory, developers can test out their flight software, their GNC processing processes by corrupting, say, certain variables that they want and see how their flight software responds to that. It's not only just a random tool that you can use to inject errors. You can specifically target variables that you want to use. That's it.
Okay. Questions?
Hi, thanks. It's very interesting, cool stuff. I was wondering if you guys, when it came to looking at injecting faults, have you looked at some of the things that are going on in the computer world for hacking attacks like Rowhammer, where you can pound on the memory and cause it to bit flip as a means of actually purposely injecting simulated or actually real SCUs for testing?
The one good thing, I have not looked into that. I might after this, but the good thing about this is that when you manually inject the error, there's no guarantee that the flight software will actually read in that corrupted data because the sensor feedback might overwrite that data before the flight software accesses it, depending on how the frequency you're running at. So this guarantees that every time the flight software accesses that variable, that you're going to read in corrupted data. So that's a good thing about having the watch points.
Yeah, this is Mike Aguilar. I think you might add to your slide in here, not only is this single event upsets with the tool suite you have, but many times you want to test out your watchdog timers. And you could use this tool to go and corrupt some instruction stream so that you can actually fire your watchdog timer without having to put some artificial watchdog timer command inside your software so you can actually test that out. It just might be something you add to your use for this tool as a test for watchdog timer corruption.
Okay, thank you. Definitely look into that. I'll have to talk to my manager, Adam.
Okay. Other questions?
Okay, thank you.